lines. Great. So, as I said earlier, in this first week, we'll sort of repeat some basics and then talk about what reason do we have to believe that quantum computers could do something better than classical. And we will look at some other sort of different modes of quantum computation. But what we'll look at first is the circuit model for quantum computation. So we assume that you have some knowledge of quantum physics already. I think much of what I'll say today will be repetition for most of you, but to make sure that we're all on the same page, it's good to mention all these things. So if you want to compute something, what do you need? You need something, some medium where you can store and represent the data. And then you need to be able to perform some operation on this data, manipulate this data to perform your computation. And then you need to be able to read out your result in it. So this blackboard is not very, it has some bad resonance. Okay, so in classical computation, to represent the data, we have bits at the most basic level. In quantum computation, we have qubits, quantum bits. And then to manipulate the data, well, we need to be able to initialize. And then we do some kind of quantum gates on these qubits. And then readout, well, it's readout. And I will not say so much about initialization and readout. It's sort of, we assume that we can we have these qubits and we can initialize them in some simple state, and we are able to do some readout on the system. So what we'll define now today is more what are qubits and what are the operations that we can do on qubits. So you all know in a classical computer, the simplest unit is the bit. It can take two values, 0 and 1. The qubit can be in all superpositions of 0 and 1. And we write this, the state of the qubit with the Kent notation. It's on state psi, which has some part in 0 and some other part in 1. And then these amplitudes, alpha and beta, are complex numbers. And they obey the normalization condition that their squares sum to 1. So we know if we do a measurement in the computational basis, that is 0 or 1, then we will get the result 0 with probability alpha squared, and we will get the result 1 with a probability beta squared. You can also write this in vector notation, where this is like alpha times the basis vector so this basis vector corresponds to the state 0, this to the state 1. So when we think about the state of a qubit, we usually visualize it with the Bloch sphere. So let's see if I can draw a sphere. We have a sphere with the radius 1, and the north pole of this sphere represents the state 0, and the south pole is the state 1. Now, the state of a qubit can be any point on the surface of this sphere. So if you take some generic point here, you can parameterize this point using two angles. One is the angle with the z-axis, take that to be theta, and then one of it is the angle with the projection. Let's see, projection comes here. Angle with the x-axis. So if we use this parameterization, then the state psi can instead be written as cosine theta over 2, 0, plus e to the I phi sine theta over 2. Why do we draw this sphere? It's because it gives us a way to visualize operations that we do on this qubit. We can, when we apply a gate to the single qubit, what does it do? Well, it will move you around on this sphere, do some rotation around some axis. It's nice to point out two more states on this sphere. So we have on the opposite ends of the x-axis, we have 0 plus 1 and 0 minus 1. And these states have their own names. These are usually called just plus and minus. I can say on the y-axis we have also 0 plus I 1 and minus on the other side. Okay, I guess most of you have. How many of you have not seen the Bloch sphere before? I think everyone has. Yes. Okay, good. So now, if we have n qubits, let me erase. So we needed two parameters here to specify the state of a single qubit. If we have n qubits, then we can have superpositions of 2 to the n states. So we have two to the n basic states, like all zeros, or first being 1, and then many more. So if we have n classical bits instead, they can be in any of these 2 to the power n different states. Keep trying to want to move this chair. I really shouldn't. Now, qubits can be in a superposition. And that, for that to specify that state, we need 2 to the power n amplitudes. Yes.
So the amplitudes are complex, right?
Yes.
So you need 2 to the power n plus 1 parameters.
Yes.
Okay.
Well.
And then minus 1 because of the normalization.
Yeah.
And then minus another one for global phase.
Yeah.
True. So this means that to specify the state of n qubits, we need a lot more than n classical bits. And this is sort of our first intuition or understanding for why a quantum computer might be able to do something better than a classical. If nothing else, it will be able to simulate quantum systems. An important application for classical computers actually is to do calculations of quantum systems like molecules and if we have quantum bits instead to do such calculations, we would need much fewer of them. And this was, as you may know, the first idea of Feynman, for example, why in the early 80s when he introduced the concept of quantum computing, it was first for simulation of quantum systems, because it's hard to simulate quantum systems. Okay, so that's a qubit. We are in this course not going to be very concerned with how we make these qubits. There are many systems or quantum systems that you can use to find such a qubit, or some two-level system, some quantum system. Superconducting qubits is what's most explored here at Chalmers. You have other techniques like trapped ions, neutral atoms, quantum dots, you name it. In this course, we are more focusing on what can you do if you have perfect qubits. So, first of all, we will see what can you do. What kind of operations can we do on a single qubit? So, single qubit gates. So, when you change the state of a qubit, you're changing from psi to some psi prime. And this operation, it needs to preserve the norm of this state. So probabilities when we measure still must sum to 1, right? So all the gates are 2 by 2 unitary matrices. Unitary because they need to preserve the norm. 2 by 2 because dimension of the space we have is 2. So we now, for these matrices, we think of this vector space. We write the state in a vector like this. And so I'll list some of the common single qubit gates. First are the Pauli matrices. So we have X and Z. So what do these operations do? Well, the X gate is the equivalent of a classical NOT gate. It will flip the qubit state. So you can see this if you apply X to psi. So we have 0, 1, 0, alpha, beta, and the result is beta, alpha. So the amplitude for the 0 state becomes the amplitude for the 1 state and vice versa. The Z gate leaves the amplitude for the 0 state unchanged and adds a phase factor -1 to the state 1. All these matrices, they can be used to generate rotations around the respective axis x, y, z on the blocks. Let's erase to make some more room. Maybe let's keep the sphere there for a while. Then we have a gate that's called a Hadamard gate. It's given by this matrix. You can actually see it's a sum of the x and z gates. So the Hadamard gate is important because it transforms one basis that we use, the 0, 1 basis, the computational basis, to the minus and plus basis on the block. Actually, it goes both ways. So if you have a state written some alpha 0 plus beta 1, you apply the Hadamard gate, you get alpha plus beta minus. And Hadamard gate, you often use it, say, if you start in some simple initial state. When you want to start a quantum algorithm, you maybe start with all qubits in 0, for example. Often you apply the Hadamard gate to create superposition states. So you will get a lot of 0 plus 1 superpositions. Okay, yes, I mentioned the Z applies this phase -1, a pi phase shift to the 1 state. There are 2 other gates that apply other phase shifts that are good to know. We have the S gate. Which then applies factor I to the 1 state. And the T gate applies phase shift pi over 4 Now, somewhat confusingly, this T gate is sometimes called a pi over 8 gate. And that is because you can rewrite it, because as someone mentioned here before, the state, it doesn't matter if you add a global phase to the state. So this is actually e to the, let's see, minus I pi over 8 times e to the I pi over 8. Sorry, no minus sign there, but a minus sign here. You can see that S gate is just T squared.
And the C gate is S squared, right?
Yes, exactly. Okay, so those are sort of the basic single qubit gates that are good to know. Let's see how we're doing on time. Okay. Might have time for more than I expected. Okay, let's move on to. I always want to move this here. Let's move on to multi-qubit gates. Unless there are other questions. So, I didn't say it before, but please feel free to interrupt me at any point if you have questions or comments. I'm going a little fast because I think most of this is something you have seen before. Yes?
Can you say why you call it pi over 8 again?
Yeah.
Pi over 8 gate?
Basically because if you break out this global phase, you have pi over 8 here and pi over 8 here.
And that brings the rotation of pi over 8 by the Lorentz.
No, so I mean, the phase, you change it, state by is pi over 4. It's just, you can write it like this, so it looks, I mean, this global phase in front, it's unimportant.
Okay.
So you have something here which has pi over 8, minus pi over 8 here and plus pi over 8 here.
Okay.
It's stupid naming convention, but it's good to know that it exists. We will just call it the T gate. Okay, so if we want to run some quantum algorithm that is going to be useful, it won't be enough that we do single qubit operations. We need to make the qubits interact with each other. And one way you can imagine such an interaction working is that you have a control gate, where the state of one qubit controls whether or not a single qubit gate is applied to a second qubit. Okay, one example is controlled knot. It's usually written C knot. It's given by this matrix. Okay, so what does this matrix mean? We are now acting on the space, state space of 2 qubits. So we have 2 to the power 2, 4 different states. So you will have the rows and columns corresponding to the 0, 0, 0, 1, 1, 0, and 1, 1 states of these 2 qubits. So what this says is basically, if you look on this in this upper left corner, if the first qubit is in state 0, then you have the identity matrix 0, right? If the first qubit, now we look in the lower right corner, if the first qubit is in state 1, then you will switch the states 0 and 1 for the second qubit. So we are applying the NOT gate or the X gate to qubit 2 if and only if the first qubit is in state 1. So 0, 0, 0, 1 don't change. 1, 0 and 1, 1 are split. So in the same way we can have control other gates. Common one is control Z gate. So then it looks like this, just ones on the diagonal and the minus ones at the end. So here again, if the first qubit is in state 0, nothing happens. If the first qubit is in state 1, then we're applying the Z operation to the second qubit. And so we'll get the phase minus 1 for state 1, 1, and all the other states are unchanged. More general, if you have some controlled unitary gate, you will have zeros here, you have identity if the first qubit is in 0, and you will apply some unitary operation U, so 2 by 2 matrix on the second qubit if and only if the first qubit is state 1. Now, the 2-qubit gate does not have to be this type, doesn't have to be a controlled gate. One example is the swap gate. So the swap gate swaps the state of one qubit into the other. So swaps the amplitudes for the 0, 1 and 1, 0 states. So that was, I would say, the most well-known, or the 2 qubit gates you should know. Then there are sort of generalizations of these to more qubits. And there are 2 that are good to have seen. So if we have 3 qubit gates, there are 2. One is the Toffoli gate, and the Toffoli gate is a C naught. So here you have 2 qubits controlling whether an operation is applied to the 3rd qubit. Maybe I should draw. So for the control knot here, let me draw the circuit symbol. So this is how you would draw the circuit for a controlled NOT gate. So you have the first qubit is represented by the first line, second qubit the second line. And here, this means, this filled dot here means that the first qubit is controlling what operation is applied to the second. So for the Toffoli gate, you have 3 qubits, and the first 2 are both controlling whether or not you should flip the 3rd qubit. So the 3rd qubit will only flip if both qubit 1 and qubit 2 are in state 1. And I will not draw the matrix here, it's in the notes if you want to see. So it will be an 8 by 8 matrix, because the state space is now 2 to the power 3. We have 3 qubits. The notes, by the way. So the notes will be available on the homepage, hopefully later today, at the latest tomorrow. It will be notes for the first few lectures, and then we will gradually update the notes. It will include the whole course. But the notes are mostly done, but not completely done for the whole course yet. The other 3 qubit gate that is often mentioned is the Fredkin gate. And this is a controlled swap gate. So we saw here the swap gate. Swap gate is over here. I can draw the symbol here also. It's 2 crosses connected by a line like that. So the control swap is simply that the first qubit decides whether we should do a swap on the second and third qubit. Now, in practice, when you try to build a quantum computer, you will have some limited connectivity between your qubits. So you will probably have nearest neighbor couplings in most cases. So it will be feasible to do 2 qubit gates, but it might be hard to directly do 3 or more qubit gates. However, it turns out that any 3 or more qubit gate can be decomposed into a sequence of single and 2 qubit gates. So if you can do single and 2 qubit gates, you can also do multi-qubit gates. Okay. So I see I'm sort of taking less time than I had feared, so that's good. That means we have enough time to discuss universality today. Unless there are any questions on this part. Okay, good. So now we have a number of gates. We might know how to do these gates on our experimental devices even. But we could ask, is this enough? Do we now have all the tools we need to perform any quantum computation that we would like to do? Maybe we don't need all of these gates. Could we perform any quantum computation just using a few of these gates? So this is a question of what is required to do universal quantum computation. So, what does universality mean if we talk about classical computers? For a classical computer, a set of gates is universal if you can apply enough of these gates in some sequence to express any Boolean function that you would like. So actually there is a 2-bit gate, the NAND gate, is universal all on its own. But you have other sets, say, to take a set and or. This is not a universal set, and you can see that by looking at how they would act. If you change an input bit from 0 to 1, in a circuit where you have this AND gate and this OR gate, you cannot change the output from 1 to 0. So if you had, for some input, you had a certain output, and then you change the input some bit in the input from 0 to 1, you can never make any bit in the output change from 1 to 0. So there's a limit on the functions you can express if you only have these gates.
They're saying you can't do a NOT gate. Does that happen?
See. Yes.
And does the set, I mean, does the number of gates that you have to apply be finite? Can I
Yes, it should be finite. For classical computers, for quantum computers, it becomes a little trickier. Now, for classical computers, it sort of is you only have these few states, zeros and one, to the power n different possible states. But we know for the quantum computer we have this continuous, there's an infinite number of states, kind of all these different points on the block. It's a continuum of states. So how do you define your universality then? Well, you say a gate set is universal if these gates can approximate any unitary transformation on any number of qubits to any desired precision. So here it's a little different. We don't need to be able to exactly represent any function, but we need to be able to approximate this function as close as we would like. So if we say I need to approximate this unitary to within epsilon, then it should be possible to apply these gates from this gate set, enough of them to eventually reach this precision. And then if you need to increase the precision, you should be able to do that by increasing the number of gates that you are applying from this gate.
Is it actually any unitary or any special unitary?
Any unitary.
Like, is like, isn't like, is it like SU4 or is it actually U4 if you do the,
So it's
like the determinant of the unitary transformation should be 1, I guess.
Yeah, well, you have.
Like, I guess it must be like more normalized afterwards.
Yeah, yeah. Yeah, I mean, it's unitary.
Is there a classical analog to this in like a probabilistic model of classical computing where you could have some epsilon approximation to a gate set in a probabilistic sense?
I don't know. For probabilistic classical computers, it's for you get the right answer with some probability. I don't know. I don't think this changes what is the universal gate set. Okay, now let's see. If we can find a universal gate set. Or rather, I would like you to tell me how a gate set can fail to be universal for a quantum computer. Is there something you could say that if these kinds of gates are not in this set, or if the gates in the gate set do not have this property, there is no chance at all of this ever being a universal gate set for a quantum computer?
They can't have entanglement, create entanglement between two.
Okay. So, entanglement you must be able to create. Is there anything else?
I guess superposition.
Superpositions you also need to be able to create, yes, because otherwise you're stuck with the states of the classical computer.
To go to any point on the block square. Like you have to be able to go, let's say, from 0 to actually any point on there, not just
Yes,
to the left. There's the 6 states you draw.
yes. I will kind of include it in the list later, but that's fine. You need to be able to explore the full state space.
Reversible.
But that's close. Oh, okay.
Is
So it's not another restatement of what is universal. But yeah, it's true.
Is reversibility also a requirement? Because quantum mechanics, or is it just like, yeah, because we are doing quantum mechanics, it will always be reversible?
Yeah, since you're doing quantum physics, it's always reversible. All of these gates are reversible, actually. All unitary transformations will be reversible.
Could it have to do with phase information somehow?
Yes. You need to be able to create some complex amplitudes. Okay, so let me give you some examples of gate sets that would fail in these different ways. So you could take the gate set of just C naught. Or a not gate also. So this would, as I showed before, you could flip 0, 1 to 1, 0, but you cannot create any new superposition state. If there is a superposition already and C naught is acting on it, then you can maintain a superposition, but you cannot create superposition. Now, if you want to be able to create entanglement, you can include the Hadamard gate. So we saw before the Hadamard gate changes the basis from 0, 1 to plus and minus. So if you have the Hadamard gate and you start in 0, you will be able to create these supposition states, 0. But you are still not, you're not going to create entanglement. The Hadamard gate is a single qubit gate. Any single qubit gate cannot create entanglement because it does not act on many qubits. Now, if we have both C0 and H, then the C0 is a 2-qubit gate. It can be used to create entanglement. And the Hadamard gate can be used to create superposition. And often when we talk about quantum physics and what makes it special, it's these two concepts, right? But that is not enough to do universal quantum computation. Because the C0 and the H gates, they both had only real entries in the matrices. They will never be able to create complex amplitudes. One way to see why entanglement is necessary to have any possibility of a quantum speedup is that if you have a product state, you can write this as a product of single qubit states. And the number of amplitudes that you need to keep track of here is just 2 times m. Which is a lot less than 2 to the power of n. So this is a state that the classical computer can simulate efficiently. But then there is one more way that we can fail, and Andreas was sort of telling us about it. That even if you have a gate set that can create superposition states, that can create entanglement, that can create complex amplitudes, that does not mean that you can do any unitary transformation. And this is the Gottesman-Nil theorem. So a quantum circuit using only these 3 things. So you can only prepare the initial state in this computational basis, 0 and 1. And you can only do measurements in that basis. And the gates you have are from the gates that are from the Clifford group. I will say what that is. that is if you take C naught and Hadamard and S, the phase gate. So this S that can give, if you remember, that was the 100I, they can give you complex amplitude. So if you have all these elements, then the circuit can be efficiently simulated. By a classical computer. So this comes down to what Andreas was saying. You can only basically visit certain points on the block sphere if you have this gate set and these conditions on the preparation and measurement. So the Clifford group is the group that map Pauli matrices onto Pauli matrices. And basically what these gates can do is to move you around between the 6 points of the block sphere that are the ends of the x. The x, the 2 ends on the x-axis, 2 ends on the y-axis, 2 ends on the z-axis. So you can only go between these points, and well, you can create entanglement between different qubits at these points. But your state space is still very limited. And it turns out that this limitation is enough that the classical computer can simulate this efficiently. So efficiently means in time polynomial in the number of qubits. So what's a universal gate set then? Here we have superposition entanglement and non-real amplitudes. Well, there are a lot of universal gate sets. I'll give you just some example. You can, for example, so we had this gate set C naught, H, and S that didn't quite cut it. But if we replace the Hadamard gate here by almost any other single qubit unitary, this will be universal. Because then you will be able to visit other points on the block sphere. So one example is take C naught, S, and T, for example.
Is it H and T? Because I mean, an S you can make from 2 T gates.
Sorry, yes.
Something else.
Otherwise, you can't go, like say, from 0 to 1 on the block sphere with only S and T gates.
Or you can't make superpositions.
You must be able to go around the X or Y axis somehow, right?
Yeah.
But the C and the T gates only rotates around the C axis.
Or those are control requirements. You can't make superposition on this. Unless you're given a superposition.
Yeah. Let's see. Let me double check actually. The notes.
But this could be a cliffhanger since we're almost out of time.
Yeah.
Clifford.
Jo, det är det som jag vill säga, men inte
I just wanted to say one sentence more, so I think we have time.
Men jag har yes, hos
Because you can go like this, and you can sort of, with like, with very many gates, you can be like very small rotation. That's why I said like to arbitrary position, just add more and more gates.
Yes, let's see. Let's remove the teeth there.
C not T and H.
Yeah, very many. Let's see. Almost anything but age. Here.
No. Almost anything like this.
But also almost anything but age.
No, like let's say we put X or Y, it will not help you.
Yes, but that is not almost not out of the gates that I will show, but you have so many other gates that doesn't take you exactly 90-degree rotations or exactly 180-degree rotations, but takes you 91 degrees or something.
But those we generally don't have names for, right?
But yeah, okay. So almost any rotation. So if you can do some rotation that is not exactly 90 degrees or 180 degrees, you're oh. And actually, almost any 2-qubit gate on its own. So the space of possible 2-qubit gates is excuse me, it's very large. So say any controlled unitary where the unitary is not some of the very simplest rotations, you will be able to actually do universal quantum computation with this type. Okay, so that was what I wanted to say today. So on Thursday we will continue to discuss, and then we've seen that we can do universal quantum computation, but we're not quite sure yet if we can do it fast and efficiently. I said we can approximate any unitary, any desired precision, but what happens if doing that approximation requires just too many gates? So that we will discuss next time. Pontus.
Yes, sorry, I didn't get the last part. What did you mean that almost any 2-qubit gate is a universal gate set on its own?
Yes. So you remember for the classical computer I showed that the NAND gate is universal, all on its own. You can construct all the other gates using NAND. And basically, if you take almost any 2-qubit gate that you can imagine, sort of outside the ones I showed you, and you apply them enough times, in clever ways, you will be able to construct any unitary transformation actually.
Okay.
It's not intuitive, but it can be shown.
Do you have anything for 3-qubit gates, like the Toffoli gate that's universal?
For classical computation, it's universal.
Not for quantum?
For quantum computation, I don't think it's universal. I can double check, but I think it isn't. I think there is some slight modification of it called a Deutsch gate. There's some control, 2 qubits controlling the third. That is universal on its own.
Thank you.
Okay. Other questions? see you on Thursday.